Well, we're talking about area. In a previous problem, we talked about how to approximate the area underneath this curve, and there was two methods for approximation. We called them the upper and lower sums, but now we're going to actually find the exact area of this shaded region here, and it's between 1 and 4, even though it's not stated here. I'm going to now state a theorem, and this theorem is good for definite integrals, and that means integrals that's been defined, and an application of this definite integral is finding area under the curve. And so let's take a look at the theorem. So this is called the fundamental theorem of calculus. F of x is continuous on the interval AB, and in this case our interval is between 1 and 4, and f of x is an antiderivative of that small f of x on this interval. So this is what we have. So we've got the interval. Here's our upper limit and our lower limit. This in this particular case is going to be our 1, and that's going to be our 4, and this is basically what the fundamental theorem of calculus says. And so in order to calculate that exact area under the curve, this is what we're going to do. And so we want to take the integral, and that means we're going to have x squared, or x cubed over 3 minus, which I should probably state here. Okay, look, by magic it's just appeared. Alright, so the integral is x cubed over 3. And now what we're going to do is we're going to find f of 4, and that means that you're going to take this 4 here, which is the upper limit, and we're going to plug it in. And so I've got it right here. We've got 4 cubed over 3, and then we go minus, and then f of 1. And 1, right, gets put in for x, and there you are. And so when we do the calculations, we get 21 square units. Now, this is the exact, which was 21. Now, in a previous problem, our lower was 14 and our upper was 29. Okay, let's take a look at this one here. We're wanting to find the area under the curve, and our function is 1 over x, and we're looking at the interval between 2 and 5. So we set up our integral, and here we put in our lower and our upper limits, and then our function f of x, and we take the integral of 1 over x, and that happens to be the natural log of the absolute value, and then we write this vertical line here and put our upper limit and our lower limit down here, and then we go ahead and evaluate. So we plug 5 in, we get the natural log of 5, and then plug 2 in, get the natural log of 2. Now, by the log properties, we could actually rewrite this. Because of this minus here, we put 5 over 2, and I just went ahead and approximated. So this is the actual approximation, 0.916, or you could say the natural log of 5 over 2. This is the actual area under the curve. So the 0.916, and it's really square units, but really in calculus, you know, we kind of leave that off. We just say the area is 0.916. We would usually not use square units. But for an application, let's say that, for example, you were pouring some concrete, and you needed to get the exact volume of the concrete that you were pouring. So if you were able to derive up a function that actually gives this curve right here, then you could get a much better real approximation than you would if you didn't know calculus. So